Hello students, welcome to lecture 17 of your course Advanced Calculus and Special Functions. In the special functions, here we are discussing the Legendre polynomial and its properties. So regarding the Legendre polynomial, in this lecture we are mainly discussing Rodrigue's formula. Actually it is alternate form to write the Legendre polynomial. Here you can see it. In fact, we call this formula Pnx equal to 1 by 2 raised to power n into n factorial and nth derivative of this x square minus 1 raised to power n. This whole thing is called the Rodrigue's formula, and you know this Pnx is the Legendre polynomial of degree n. So we have to show that this Pnx can be written as like this, and this will be called a Rodrigue's formula. So from the definition of the Legendre polynomial, we know that Pnx is equal to summation n going from 0 to n by 2 bracket, and the meaning of this n by 2 bracket is this thing is equal to n by 2 if n is even number, and it is equal to n minus 1 by 2 if n is an odd number. Now you want to establish this formula here. So let us start with the right hand side of this formula. You can see there is one term x square minus 1 raised to power n. We can open this term using the binomial theorem. You see, x square minus 1 raised to power n can be expressed as summation r going from 0 to n raised to ncr x square raised to power n minus r into 1 minus 1 raised to power r. When you simplify this, you can get ncr minus 1 raised to power r and x raised to power 2n minus 2r. In fact, when this 2 is multiplied with n minus r, we are getting like this. You know, the simple form of this is, if you have the expression of this form, x plus a raised to power n, then using the binomial formula, you write nc naught x raised to power n a raised to power n a raised to power 0. Then further we have nc1 x raised to power n minus 1 a raised to power 1 plus nc2 x raised to power n minus 2 a square, and so on so forth. Likewise, the last term in this expression comes out to be ncn x raised to power 0, then a raised to power n. If we write this expression in compact form, we can write it like that: summation r going from 0 to n ncr x raised to power n minus r into a raised to power r. So in this case, you can see that in place of x we are having x square, and in place of a we can write minus 1. So in this way, from this formula, we are able to write this x square minus 1 raised to power n equal to this quantity. Okay, now in right hand side, you require the nth derivative of this quantity, with respect to x, and this additional factor is there, 1 by 2 raised to power n into n factorial. So let us see what it can give us. Because we have obtained that x square minus 1 raised to power n is equal to this expression, this summation on this side. When we are multiplying, when we are taking the nth derivative with respect to x on both sides and multiply with this factor 1 by 2 raised to power n into n factorial, what do we get? In the left hand side we are getting this thing, so same thing we are applying here: 1 by 2 raised to power n into n factorial, the factor is here, and then the nth derivative on right hand side of x, of the term containing this variable x. So we are taking the nth derivative over here. So let us see what it can give us. You know, the nth derivative of x raised to power m equal to 0 if m is less than n. You can easily see. Suppose I am having here x cube and I'm taking the fourth derivative, of course it will give you 0, because here m means 3 is less than n, that is 4. So it will happen like this. But what happens when m is greater than or equal to n? In that case, you can easily see when you differentiate it again and again, and you differentiate it, this n times, you can get m factorial divided by m minus n factorial into x raised to power m minus n. You can verify this. You can verify this by taking the powers here value of m or n, but m should be chosen in such a way that it should be greater than or equal to n. So this formula comes out. Okay, but now in our case, we have to take the nth derivative of this. In fact, in place of m, we are having 2n minus r. So we can find the derivative here in such a way that the nth derivative of this x raised to power this quantity equal to 0 if the power is less than n, because of this fact. That is, if you simplify this, that is r is greater than n by 2. So here we can say the nth derivative of this term, nth derivative of this x raised to power 2n minus r is 0 when r is greater than n by 2. R is greater than n by 2, because here now in equation 3 the value of r is varying from 0 to n, so of course n by 2 will be before n. So in fact, when you take 1, 2, 3, etc., somewhere you will be having n by 2 and then n by 2 plus 1 and so on so forth, and then you will be having n. So in fact, if we break this whole summation when r going from 0 to n by 2 and when r going from n by 2 plus 1 to n. So for the values when r is greater than n by 2, the expression gives you 0. That means this derivative gives you the 0 value, and consequently all the terms where r is greater than n by 2, the value is 0. Therefore this summation can give you some value only when r is varying from 0 to n by 2. In this way we can write this in place of this summation r going from 0 to n. In fact, we can write 0 to n by 2. But again, it depends on whether n is even or odd. Because if it is even, then n by 2 gives you some integer. But when it is odd, then in place of this n, it should be n minus 1 by 2. So that way, the limit or the values of r must vary from 0 to n by 2 bracket here. Hence, this equation 3 reduces to the form you can see in the left hand side, 1 by 2 raised to power n into n factorial, nth derivative of x square minus 1, in fact this is raised to power n, equal to 1 by 2 raised to power n into n factorial, summation r going from 0 to n by 2 bracket. In fact, this bracket means you already know its value is n by 2 when n is even, and its value is n minus 1 by 2 when n is odd. Fine. So this term remains as such, only we have neglected the term for which r is greater than n by 2. So we are getting this kind of expression. Okay. Now 1 by 2, further you see in this equation, 1 by 2 raised to power n n factorial, summation r going from 0 to n by 2 bracket, ncr minus 1 raised to power r. Now let us see what is value of this x square x power 2n minus 2r. So now we should consider this formula, because in this case you have that m is greater than equal to n. So in that situation, what can we have over here? You write it in this way, 2n. In fact, in place of m we are having 2n. In place of m we are having 2n minus r. So here you can write 2n minus r factorial, and in place of m again you write 2n minus 2r minus n factorial, and here it must be x raised to power m minus n. So what is there in place of m? M means in this case is 2n minus r. So here you will write x raised to power 2n minus 2r minus n. In place of this n is there. So in this way, we can have the value of 1 by 2 raised to power n into n factorial, and as the derivative of x square minus 1 raised to power n comes out to be this quantity. Now the further simplification can give us, you take this 1 by 2 raised to power n factorial inside the summation, you can have 1 by 2 raised to power n factorial. Then if you open this NCR, the value of NCR is always, n factorial divided by r factorial into n minus r factorial. So we have opened this NCR. So NCR is giving us n factorial r factorial into n minus r factorial. Minus 1 raised to power r is there, and this 2n minus 2r is there factorial, and after simplification 2n minus n gives us n, so it remains n minus 2r factorial. Now let us have a look at this term. This is nothing but the expression of Pn, as we know from the earlier definitions. So we have established that this quantity is equal to Pn, and this is what we call as the Rodrigue's formula. That is, Pn is equal to 1 by 2 raised to power n factorial, nth derivative of x square minus 1 raised to power n. So this is the proof of the Rodrigue's formula. Next, now let us find the values of these Legendre polynomials of degree 0, degree 1, and degree 2, degree 3 using the Rodrigue's formula. From the Rodrigue's formula, we know that Pnx is equal to 1 by 2 raised to power n into n factorial, and at the derivative of x square minus 1 raised to power n. So this is equation 1. Now we want to find P naught x. So how we can find it? Put n equal to 0 here. Very simple. P naught 1 by 2 raised to power 0 and 0 factorial. 0 means we are not going to take any derivative. You simply are having this term x square minus 1 raised to power 0. So anything to the power 0 gives you 1, and here 1 and 0 factorial is also 1, so you can say that P naught x is 1. You already know from the earlier calculations that P naught x is 1 always. Now if you put n equal to 1 in this equation, when that means we are getting P1. So here 1 by 2, 1 factorial, the first derivative of this, and here n is 1. So in fact we are getting 1 by 2, 1 d by dx of x square minus 1. So this gives you 2x. 2 goes with 2, so the value is x. So P1x is in fact equal to x. Now by putting n equal to 2 in 1, we have P2x is equal to, again you are putting n equal to 2 here, so 1 by 2 raised to power 2, 2 factorial, the second derivative of x square minus 1 square, because you are taking n equal to 2. So it is very simple calculation. You can do it, and you can find it that the value of P2x comes out to be 1 by 2 into 3x square minus 1. Similarly, when we substitute n equal to 3 in equation 1, we can obtain the value of P3x, and the value of P3x comes out to be this thing, 1 by 2 into 5x cube minus 3x. So this was one exercise based on the Rodrigue's formula. Now next exercise 2 is there. The integral of P and x between minus 1 to 1 gives you 2, the value equal to 2, if you take n equal to 0. The second part, the integral of P and x from minus 1 to 1 comes out to be 0 whenever you take n greater than equal to 1. So let us establish it. Okay, so first we consider n equal to 0 in the first case. We are solving the first case. When we take n equal to 0 here, you can see when p naught is there, you already know that p naught x is 1. So in place of this, you can write here 1. So dx means x, and derivative of integration of this gives you x. In fact, the value is x, and limit is from -1 to 1. That gives you 1 minus of -1. In fact, that is equal to 2. So we have proved the first case. Now let us prove the second case. When you are taking n greater than equal to 1, you know -1 to 1 pnx dx is equal to 1 by 2 raised to power n factorial from the Rodrigue's formula, from the Rodrigue's formula. And dn stands for this, the nth derivative, dn divided by dxn. So for the sake of convenience, we are writing here dn. Dn in fact stands for the nth derivative of this. So that was the value of pnx, and integration is taken here. The term independent of x are taken outside. 1 by 2 raised to power n factorial are taken outside. So you are integrating it, in fact. So when you integrate it with respect to x, you can see that if we have n times derivatives, so one derivative cancelled with one integration, and it becomes n minus 1th derivative, and you are taking the limit from -1 to 1. So when you are taking the limit -1 to 1, before that we are just simplifying this term. Actually, it reduces to x square minus 1 becomes x minus 1 and x plus 1, and power is n, so these power are, when separated, it comes out to be like this. And the limits are -1 to 1. Okay, now just you have to focus on this part carefully. There is one Labness theorem. Before moving on to the second line of this proof here, I would like to mention Labness theorem. Labness theorem in the differential calculus is nothing but it gives you the nth derivative, or n minus 1th or n minus 2th derivative, etc., of the product of two functions. In fact, in simple form, we can write that you want to find the, suppose you are having two functions u and v, both are functions of f, and suppose I am writing here n. N stands for the nth derivative. In fact, dn dx n uv. I am giving you this another notation, u dot v, and n here subscript denoting the nth derivative of this product of two functions with respect to x. So using Lebanese theorem, in fact, you should remember it. How we find the nth derivative of product of two functions is like that. Nth derivative of second function as it is. Second term will be nc1 n minus 1th derivative of first function and first derivative of second function. Then you come to nc2 n minus 2th derivative of first function and the second derivative of second function. Like that, we move further, and ultimately we have ncn first function as it is and the nth derivative of the second function. The alternate way to write this Leibniz theorem is here. You can see here we are taking the nth derivative of this product of two function is dnu, means the nth derivative of u. This thing and this un meaning is same. Into v is there, nc1, then n minus 1th derivative of u and the first derivative of v. In the next term you will have n minus nc2, n minus 2th derivative of u and the second derivative. In fact, here it will become d square v, or we simply write v2. And in the last, it is nc1, ncn. Actually, value of ncn is 1. So we are having NCN is 1, u as such, and the nth derivative of v, that is v, and we can write it like this. So the Leibniz theorem is used to find the nth derivative of the product of two functions. Suppose we want to find the n minus 1th derivative, then how it will reduce? When you want to find the n minus 1th derivative, how it reduces? It reduces in this way. We have to write here in place of d, in place of this dn by dxn, we should write here dn minus 1 and dxn minus 1. Similarly, here it would be n minus 1. So exactly just by replacing n with n minus 1, the whole thing will be calculated here. In place of this, you will write un minus 1. That means the n minus 1th derivative of u, first derivative of v. Then here you will write n minus 1 c1. Here it will be n minus 2. Here it is v1. It is n minus 1 c2. It will be n minus 3. And this is v2. And like that we can find. Finally, also we will have n minus 1 cn minus 1 when you are going to find the n minus 1 derivative. So this I am telling because here in this case, what is happening at this step, this is in fact u and this is in fact v. And this is the n minus 1th derivative of product of two functions now. So you should apply here the Labness theorem of the differential calculus. So that will give you the term outside this bracket remains same. Now in place of u, you are having this. So what you do, you will take the n minus 1th derivative of this term, n minus 1th derivative of this term, and the second term remain as such. Then you are having n minus 1 c1, n minus 2th derivative of first term, and first derivative of second term, that is this is v1, and so on and so forth. Finally, we shall have the first term as it is. In fact, this is u and n minus 1 a derivative of the second term. Okay, on simplification using this formula, from here the first term will become, when you take the derivative of this term n minus 1 time, in fact it give you take the first derivative, you will get n into x minus 1 raised to power n minus 1. When you take the second derivative, it becomes n into n minus 1. When you take the third derivative, it becomes n into n minus 1 into n minus 2 into x raised to power 1 raised to power n minus 3, and so on. Means you are getting n into n minus 1, n minus 2, and so on up to 1. So that gives you the n factorial. And at the n minus 1th derivative, it remains only x minus 1. Now this term will remain as such because v you have to keep as such in the first term. Like that, when you simplify all the terms here, you will get n factorial. Suppose we are finding it the last one. So in the last one also, you will take the nth derivative of this, in fact nth derivative of this, and this term as such x minus 1 raised to power n. So in all these terms, in this when you simplify this, in all these terms you will have the term x minus 1. This you are going to have this product x minus 1 into x plus 1. Only powers will be different. But when you put the limit x, the upper limit 1, so because of this factor all the values will be 0, and then the lower limit, because of this factor all the values will be 0. So ultimately this whole expression comes out to be 0. In this way, what we have proved? We have proved that the value minus 1 to 1 pn x dx, this gives you 0 when n is greater than or equal to 1. So that is what we wanted to prove. Now the exercise third. In third exercise, we have to show that if this m is greater than n minus 1 and n is a positive integer, then prove that integral 0 to 1 x raised to power m pn x dx is equal to m into m minus 1 into m minus 2 up to m minus n plus 2 divided by m plus n plus 1. into m plus n minus 1, and so on up to m minus n plus 3. We have this term. So we can prove the right hand side by using the Rodrigue formula in the left hand side. Using the Rodrigue's formula, in the left hand side we have 0 to 1 x raised to power m p n x. In fact, in place of p n x we write the value. The Rodrigue formula is 1 by 2 raised to power n factorial. X raised to power m will remain as such, and the nth derivative of this term, this, you know, the Rodrigue formula, value of p n x we have substituted over here. Okay. Now we can take the integration by part. We can take the integration by part here. You can consider this function as the first function and this as the second function. Then you integrate by part this integral. First function as it is, and integration of second. Integration of second give you the one derivative will be cancelled out. It will remain the n minus 1 at derivative, in fact. So dn minus 1 x square minus 1 n, and limit are taken 0 to 1. Minus, in the integration by part, we take the derivative of this. This is m into x raised to power m minus 1. M is there, and integration of second part again. When you integrate the second part, we are having this thing. So here you can see when you put upper limit 1, so it gives this part give you 0. When you put lower limit 0, then part 0. So the whole first part reduces to 0, and we are left with minus 1 raised to, because here we are having this minus term. So minus 1 raised to power 1 m, and this 1 by 2 raised to power n factorial, these values are taken, and inside the integral we are having 0 to 1 x raised to power m minus 1 and n minus 1 at derivative of this term. So in the integral we again apply the integration by part rule, and for the second term again we are using, then we are getting the first term like this and the second term like this. You know, this term again will be 0, and when you take this term and multiply the whole thing outside here, we get minus 1 raised to power 2m into m minus 1 divided by 2 raised to power n factorial, and this integral again. Now the first term is again 0 as shown in you know, that's exercise 2 here. Then now you see, when we applying the continuing in the similar way up to n minus 2 times, then we are going to have, at the next step you will have m minus 2 here, and here it will become m minus 3, and it will become n minus 3, and so on. So when we continue these steps up to n minus 2 times, then we'll have the expression of this type. Outside the integral we will have these kind of terms, and inside we shall have x raised to power m minus n, x square minus 1 raised to power n dx. Okay, now we further simplify this term. We are having 0 to 1 x raised to power m minus n, minus 1 raised to power n is there. We are taking it inside, and in fact not taking inside, we are taking minus 1 common from this part, so we are getting minus 1 raised to power n, and it becomes 1 minus x square raised to power n. Now if we substitute here x square equal to t, so that 2x dx gives you dt. So in fact, in place of dx you can have dt by 2x, but you know this value of x square is t, so therefore the value of x is equal to t raised to power 1 by 2. So in place of dx we write dt by 2 raised to power 1 by 2, and in place of, you know, this x is t raised to power 1 by 2 and power is m minus 1, and here 1 minus t raised to power n. Why we are writing it in this manner, you will come to know in the next step. See, after simplification we can write it as 1 by 2. When you take t by 2 in the numerator here, so it becomes t raised to power 1 by 2 into m minus n minus 1, and here 1 minus t raised to power n dt. The outside term is here. Then 0 to 1 t raised to power this, we can further simplify this in this form. 1 by 2 t raised to power 1 by 2 m minus n plus 1 minus 1. We can write this in this way. And similarly 1 minus t raised to power n, we can write it in this way, n plus 1 minus 1. Why we are writing it in this manner? Because we have the formula of beta and gamma functions. In beta and gamma functions, you know, the beta function is written in this way. You see this. When we have the integral 0 to 1, some variable to the power p minus 1, and 1 minus that variable to the power q minus 1 dt, then this integral is equal to beta pq, and this is called the beta function. This is called beta function. So in our case, we have written t raised to power, 1 by 2 m minus n plus 1. In fact, this is in place of, this part is in place of p, it is p minus 1, or in place of q, here we are having n plus 1, so this is in place of q. So 1 minus t raised to power q minus 1. So value should come out to be beta pq. So in place of p is this quantity, in place of q is n plus 1. So in that way we could write it as beta pq, but this beta pq is in fact gamma p, gamma q, and gamma of p plus q. So in place of p, as I mentioned, is 1 by 2 m plus, in fact, let us see, this is m minus n plus 1, this is m minus n plus 1, okay, and in place of q here we have seen is n plus 1. So it becomes beta of 1 by 2 m minus n plus 1 and n plus 1. But beta pq is equal to this quantity. So meaning of p is this thing and meaning of q is n plus 1. So using this formula, gamma p, gamma q divided by gamma p plus q, we can have this gamma p is this quantity, gamma q is this quantity, gamma of p plus q is this quantity. Okay, now again we have the formula that gamma of p plus 1 can be written as p into gamma p. So using this fact, this n gamma of n plus 1 can be written as gamma of n plus 1. One more formula is there. When we are having gamma of n plus 1, that should come out to be n factorial. Here is the formula, and this formula is can be derived from here. You repeat it again and again, you can obtain. In place of p, if you write n, so we'll get n into gamma n. Further, when you open gamma n, it gives you n minus 1 outside, and here n minus 2, and so forth. So in this way you can obtain gamma n plus 1 can be reduced to n factorial. So in place of gamma of n plus 1, we are writing here n factorial, this term as such, and when you add the values here, we can get gamma of m plus n plus 3 divided by 2. Now for the cancellation of the term, because in our proof we don't require this gamma function, so we have to simplify this gamma function. In fact, the gamma function in the denominator is having the value, more value. This is m plus n plus 3 by 2, but here it is m minus n plus 1 by 2. So this is the lower quantity and this is the higher quantity. So the higher can be reduced to the lower again and again. So using this form, suppose you are having gamma p plus 1, so it can be written as p into gamma p, means you can just subtract 1 here and the rest of the things you can write like this. Okay, so from m plus n plus 3 by 2, if you subtract 1, so what do you get? M plus n plus 3 by 2 minus 1. So let us see what we have. We'll have m plus n plus 3 minus 2 in fact. So that gives you m plus n, and 3 minus 2 is 1, plus 1 by 2. So in fact, in place of this, I can write m plus n plus 1 by 2 into gamma of m plus n plus 1 by 2. So m plus n plus 1 by 2 into gamma of m plus n plus 1 by 2. So m plus n plus 1 by 2 is here. That means this thing. And into gamma of same thing must have been written. But again, that gamma of m plus n plus 1 by 2, again when we subtract 1 from there, then this term will be obtained. Again we subtract, ultimately like that we continue up to n terms, up to n plus 1 terms here. So we get this term finally, and the same term will remain with the gamma function. Now you can see the gamma function in the numerator and gamma function in the denominator will be cancelled out. Now you can see this 2, 2, 2, 2, it will be up to n plus 1 times. So this is 2 raised to power n plus 1 time in the denominator, and here 2 raised to power n plus 1. These will be cancelled out, and we are left with m into the upper one, the numerator. You can see m into m minus 1 and so on up to m minus n plus 1. So this is the numerator, and in the denominator we are going to have m plus n plus 1, m plus n minus 1, and m minus n plus 1. So this is the expression we wanted to prove. So this is about the Rodrigue formula and the numerical problems based on the Rodrigue formula. Some more problems can be there of this kind. You just have to simplify the integration or differentiation. That is it about this lecture. Thank you.